All righty, what's up, friends? How are we doing today? So we spent the last couple days talking about simplifying expressions. So today we're going to talk about the parts of the function itself. So that's really where we wanted to get to. So there's a few things we're going to talk about today. We're going to talk about vertical asymptotes. We're going to talk about horizontal asymptotes, and we're going to eventually talk about slant asymptotes. We're going to talk about zeros. We're going to talk about y-intercepts. And then the last thing we're going to talk about are holes. So these are essentially the big ideas and that we're going to be playing with. Now, one of the things you need to realize, and we'll talk more about it when we get there, is this idea of a slant asymptote and a horizontal asymptote. They can't happen at the same time. It's either going to be one or the other. Now, a vertical asymptote can show up whenever, but a horizontal asymptote cannot show up when there's a slant asymptote, and vice versa. So it's one or the other. So let's go back and remember what an asymptote is. It's that x value that you get really close to where your graph goes off to infinity. It kind of shoots up really high up. Now, you guys probably said that it's an imaginary line that you get really close to but never touch. And okay, in a practical sense, that's kind of what it looks like. It's not exactly what it is, but it's kind of what it looks like. And the way we get a vertical asymptote is we take the denominator and we set it equal to 0. So here's our denominator. We set it equal to 0. So whatever makes the denominator equal to 0, that's our vertical asymptote. In other words, we'd say that that is the line that we get really, really close to, but never, ever, ever reach. So, and again, I don't know what the rest of the graph looks like. I'm not going to worry about it as of right now. But essentially, what ends up happening here is we get something really close to what the graph looks like. It gets really close to that x value, but it never reaches. Instead, it goes off up towards positive infinity here, or it goes off where the y value approaches negative infinity. Okay, some x value where it goes off into infinity. Likewise, sometimes it's not as simple as just figuring out what makes our denominator equal to 0. For instance, if you notice here, on the second one here, we have a vertical asymptote at 4. However, x plus 3 would not be a vertical asymptote because it also has that factor in the numerator. If the factor is in the numerator or the denominator, that's how we get the value of a whole. So we still set our vertical asymptote, our factor in the denominator, equal to 0. And we find a vertical asymptote of 4. So let me go ahead and graph this a little bit so you can kind of see what it looks like. All right. And again, this is a real rough sketch. I should be drawing a dashed line for that asymptote, but I'm not going to. But when x equals -3, what ends up happening is that my graph does some really kind of weird. So let me talk briefly about what this looks like so we kind of get the gist of what a hole is. So if I have x plus 3, we can see that that x plus 3 factor is in both the numerator and the denominator. Now, when we were simplifying rational expressions, we said, let's just go ahead and cancel that factor out. But with functions, while we'll still cancel it out, we have to make a very important distinction here. That remember, just like when we were dealing with composition of functions, when we put two functions together, whatever was in the original domain still has to be true. So even though this x plus 3 is in the top and bottom getting canceled out, I still have to remember that because I couldn't use x equals -3 to begin with in the original function, when I cancel it out, that still is going to be true. I still can't use x equals -3. Even though it's no longer a factor in my new denominator, it was a factor in my original denominator. And since it was a factor in my original denominator, I have to make sure that I still don't use that value. Now, if you notice this new function, if I were to plug -3 in there, I end up with 1 over -7. So at that point, -3, my graph is going to look like it gets really close to this y value of -1,7. However, there's something that happens there. And what happens there is what we call a hole. In other words, the graph is going to look like it's going to get really close to some value here, but the graph will have like a little hiccup, a little blip in time where the graph doesn't end up becoming. So I drew that on the wrong side. That graph doesn't end up becoming -1/7. It gets really close, but that little blip doesn't allow it to happen. So instead, the graph looks like this. It kind of comes up here. And if you graph on your graphing calculator, you're not really going to be able to see it because, again, it's just like this little wormhole type idea. It's just a real small sliver where the graph kind of goes away. It has this little hiccup, this little break. Well, it's not an asymptote. It's not a vertical line we don't get to. It's like this little opening that it just kind of essentially breaks. It's for lack of a better phrase, it's this little opening in our curve, in our function, that that it looks like it exists, but if you zoom in on it really, really closely, you'd see that there is quote unquote a hole there. That's where a hole comes from. It comes from the x value. Comes from the x value of what was canceled out in both the numerator and the denominator. It's the factor that cancels out. That gives us the x value of our hole. It's not a vertical asymptote. It's the x value of a hole. The vertical asymptote. So again, come back to the problem we were working on. This is our vertical asymptote right here, that x minus 4, since it only resided in the denominator. But this x plus 3, that will give us the x value of a hole because it crosses off the top and the bottom. Okay. And again, if we keep going here, notice on the third one here, we can actually have more than one vertical asymptote. We can have more than one. That's okay. We can have more than one. So we have this idea of a vertical asymptote. It's whatever makes a denominator equal to 0, except when the factor in the denominator is also in the numerator, then that's no longer a vertical asymptote. That's the whole of the function. So let's keep going here a little bit. And here's the idea of a hole right here for you again. You can kind of see what we're talking about. It's that factor that exists in the numerator, but also happens to exist in the denominator. That gives us the x value of our x, and when you plug it back into that new function, notice right here, they took out that factor and they canceled it out, and that left them with 1 over x minus 1. So when they plug the -4, that canceled out factor in, they get the y value for it. Okay. And at the same time, if you notice as well, there was still a factor that was left over here in this problem. So that became the vertical asymptote. Okay. And we've already kind of covered holes already. So let's keep going here a little bit. The next part is the horizontal asymptote. Okay. Horizontal asymptote. Now, there's going to be 2 different times you can have a horizontal asymptote. And it has to deal with the degree of the function. If the degree of the function is bigger in the denominator than the numerator. So what you remember here is denominator is greater than numerator. When the denominator is greater than the numerator, we're talking about degree here. The denominator is greater than the numerator. The vertical asymptote or the horizontal asymptote, is y equals 0. If the degrees are equal, in other words, the denominator equals the numerator, when that happens, our horizontal asymptote, that horizontal line we get really close to, equals the leading coefficient divided by the leading coefficient. So how does this apply to us? How's this going to work? Let's look at these examples real quick. So first of all, that's a 1. Notice the degrees. The degree on top is 1. The degree on the bottom is 2. Since the denominator is bigger, the horizontal asymptote is 0. On this other one here, the degree on the top is 2. The degree on the bottom is 2. So that means the horizontal asymptote is the leading coefficient divided by the leading coefficient. 3 divided by 5. What a horizontal asymptote is, and this is, again, something that's kind of not understood real well. What a horizontal asymptote is if I have some vertical asymptote, we'll go ahead and draw it right here. A vertical asymptote. What a horizontal asymptote is, and let's take this y equals 0 one, is if I were to draw it, that means my graph gets really close to this line y equals 0. My curve does. So, and what ends up happening is my graph would essentially get really close to that function. And again, I'm not worried about if I graph this right or not. It gets really close to that function as I go to negative infinity, or it gets really close to that horizontal line. The function gets really close to that horizontal line. It never reaches it as I go to positive infinity. Biggest thing to remember on this is it only occurs as you go to negative infinity and as you go to positive infinity, out at the tails. It doesn't occur in the middle. So for instance, let me draw another graph here. Say I have a graph that has 2 vertical asymptotes. And again, you guys dealt with this last year, I believe, in integrated 3, but if you didn't, that's okay. We're going to cover a little bit here. Say I have a vertical asymptote here and a vertical asymptote here. And again, I have some sort of horizontal asymptote. We'll make it right here at the x-axis again, really close to it. Now, my graph, I could have a graph get really close to that y-intercept, or that horizontal axis there, because it approaches negative infinity. I could have my graph get really close to my horizontal axis over here because it approaches positive infinity. So my graph would have the asymptotes out on the outside. But notice, if I have more than one vertical asymptote, I can't get to negative infinity this way. I get stopped by that asymptote. Can't get to positive infinity this way. I get stopped by this asymptote. Because of that, if I have a section inside, it looks like I can cross the horizontal asymptote. What you need to understand by that is that horizontal asymptote, it was never there. Okay? That horizontal asymptote's never in between 2 vertical asymptotes. It only exists if I can get to infinity. In other words, my asymptotes can only exist from the vertical asymptotes out. They don't exist inside 2 vertical asymptotes because I have to reach infinity. So again, if the denominator has a bigger degrees in the numerator, the asymptote is 0. If the denominators have the same degree, the horizontal asymptote is leading coefficient divided by leading coefficient. The question comes up, what happens when the degree in the numerator is bigger than the degree in the bottom? What happens if the numerator is greater than the denominator? Well, that's called a slant asymptote. And again, you can see kind of why you can't have a slant asymptote and a vertical or horizontal asymptote at the same time, because both of them deals with the degrees. So if the numerator is larger than the denominator, then I have a slant asymptote. Okay. Now, a slant asymptote, that occurs when that happens. The way we find it is by dividing. When we divide whatever, so notice how we have this x minus 2. Looks like Ms. Hodge is dividing that into 2x squared minus 5x plus 5. So she's using her synthetic division. Notice what happens here. When we divide, we always end up with a remainder. Well, if we end up with a remainder, that means that I'm going to end up with some other part, 2x minus 1. Remember, if my degree is 2, when I write the result here, I get x, so 2x minus 1. It means that I'm never going to reach this expression right here. So I'm never going to reach that expression y equals 2x minus 1. And again, we're going to see all this here in a second to help it make a little sense here. So that, because I have a remainder, that means I'm never going to reach what happens before. So that would end up being a slant asymptote. So this is going to be kind of what we play with today. All right, and it's going to be a little bit longer. We had a couple short ones ahead of time, but we're going to get something a little bit longer today. So what I'm going to ask that you guys do on this is we're going to come up with the vertical asymptotes, the horizontal asymptote, the slant asymptote. Again, you can only have the horizontal or slant, can't have both. We're going to have the zeros of the function, including multiplicity. We're going to have the y-intercept. And we're going to also have the poles, if there is one. So that's going to be kind of what we're playing with today. Okay? So let's see how this works. First up, vertical asymptote. Now, before I set my denominator equal to 0, I have to first factor my numerator. So f of x equals x squared. Oopsies. I do my factoring here. X minus 4, x plus 1, all over x plus 3. I want to color coordinate this just a little bit to help ourselves out here. So we look at our factors. Do any of them cancel out? And we'd say no. So that means the vertical asymptote is going to exist when my denominator equals 0. So x plus 3 equals 0. That means x cannot be equal to negative 3. So I have a vertical asymptote, but x equals negative 3. I can go ahead and do my zeros as well. So let's go ahead and do that. My zeros come from setting my numerator equal to 0. So x minus 4 equals 0. And x plus 1 equals 0. So x equals 4. and x equals -1. Well, those will be my zeros. So 4, 0, and -1, 0, those would be my x-intercepts. Notice how each one of them only has a multiplicity of 1. Notice as well, I had no factors that ended up canceling out. Since there are no factors in the numerator, they cancel out the denominator. No common factors, that means I'm not going to have a hole here. So we're not going to worry about that here. Next up, we have our y-intercept. So to find the y-intercept, I'm going to plug 0 in for my function. So if I plug 0 in for my function, I get 0 squared minus 0. So I end up with a -4 over 3. So I plug 0 in for all these x's here. And I end up with -4 over 3. So that means my y-intercept here is 0, -4 over 3. And by doing all this, friends, by coming up with all this stuff, we're going to be able to make a pretty rough sketch of what this graph looks like. Now, it's not going to be perfect, but it'll be a pretty rough sketch. All right, now the last part, the part that we were kind of struggling a little bit with. This is where we're going to look at our asymptotes, horizontal or slant. And so we're going to go through and we're going to compare the degree. That is a 1. So we compare our degrees. The numerator is 2. The denominator is 1. So for the horizontal asymptote, I probably should have put that I did the y-intercept here. Let me write that in real quick. So for the horizontal asymptote, when I'm looking at the degrees, I see that 2 is greater than 1. In other words, the numerator is greater than the denominator. What that tells me then is that there is no horizontal asymptote, and instead I have a slant asymptote. So I'm going to have to use division here to figure out what that slant asymptote is. So x plus 3. So since I do not have a horizontal asymptote, I have a slant asymptote. And we're going to have to do our synthetic division or polynomial long division. If you want to use the box, do it. If you want to actually use polynomial long division, go for it. I have to use my polynomial division to figure out where my graph cannot cross. So remember, since I know my numerator is bigger than my denominator, I'm going to end up with some sort of remainder, which is totally good. So I'm going to add going down, multiply by the box going up. Add going down, box going up, and I end up with 14. So again, if you recall here, I have a remainder, so it's not a factor. That's why I have a slant asymptote. So that, therefore, I can turn this into, I'm going to go from a square down to something to the first. So that means this right here is my slant asymptote. Y equals x minus 6. That would be my slant asymptote when I graph this. So we're going to make a rough sketch now. What does it look like? Move that axis up a little bit, huh? There we go. Oh, 7, 8. So now we're not going to be exact here. We're not going to try to be exact. We're just going to try to see if we can't come up with an idea of what it looks like. So I have a vertical asymptote at -3. So -3. That's going to be that vertical, that x value that I get really close to, but I never reach. That's when the graph goes to positive or negative infinity for the y value. Okay. I have a slant asymptote at y equals x minus 6. So let's see here. That'd be right about here. I'm going to draw my slant asymptote. I have zeros at 4 and -1, so we're going to graph those on here. -1, 4. I had a y-intercept at 0, -4/3. So that'd be right about here. And it means my graph then is going to look something kind of like this. I'm going to come down really close and go out that direction. And if I were to graph it, I'd also notice that there's going to be another little part that's going to be down here in this little quadrant. Notice how they're kitty corner from each other. Okay. So that's what we're doing today. We're going to be graphing asymptote 0, y-intercept, whole, and then making a sketch. Once you guys go down to number 2, all right, and for those of you that can't see number 2, if you didn't print up your notes, it looks like this. F of x equals, it's like x squared minus 1 all over x squared minus 2x minus 3. So why don't you go ahead and pause the video and see if you can come up with your vertical asymptote, your horizontal asymptote, your slant, your zeros, and your whole. Go ahead and pause it now and see what you guys come up with. Probably thinking I should just have cleared the screen and just rewrote those titles, but that's all right. I like playing with magic eraser there. There's our graph right there. Here we go. All right. So we said before we do anything, got to factor it, see what it looks like. Because if we have to see if anything is going to cross off here. So what do we got there? We got x minus 1, x plus 1. We have x minus 3. And we have x plus 1. And if you notice, I see a factor that's going to go away. So that means my f of x, I can get rid of those x plus 1s. So this really is the function that I'm dealing with here. But it's important to remember, I have an x value that doesn't work. So I'm going to leave that right here. That -1 didn't work because I was able to cancel them out. All right, so let's try this here. Vertical asymptote. I'm looking for whatever is in the denominator. Whatever is in the denominator, that will give me my vertical asymptote. So x minus 3 equals 0. X equals 3. I always deal with the horizontal asymptote and the slant asymptote last. That's just me though, because for me, it can get just a little bit complicated. So I'll keep going here. Next up, I have my zeros. I only got one factor left over. So if I plug my one numerator, make it equal to 0, I get the 0 of my function, which is 1. That means I have an x-intercept at 1, 0. This has a multiplicity of 1 as well. All right, the y-intercept, that's when I plug 0 into my graph, or into my x value, sorry about that. All right, so f of 0, that gives me 0 minus 1, all over 0 minus 0 minus 3. So my y-intercept is going to end up being 0 and 1/3. Negative divided by negative is a positive. My whole, well, I have one this time because I had an excluded value. So to find out the y value that goes with that whole, I'm going to plug 1 in, or negative 1 in, I guess. So I have negative 1 minus 1. And I have negative 1 minus 3. So negative 2 over negative 4. That means I'm going to have this little blip in time at x equals negative 1. It's going to happen at 1/2. So when I graph that, I'm going to graph it with an open dot because that's where my graph has this little tiny opening. All right, here we go. So it brings us to our degrees. Do we have a horizontal asymptote or do we have a slant asymptote? So for my horizontal asymptote, I have 2 divided by, or 2, which is equal to 2. That means my numerator equals my denominator. So that means my y-intercept then is going to be the leading coefficient divided by the leading coefficient. So what are the leading coefficients? Well, I don't see any numbers there, so if there is no numbers there, we assume it is just 1. So my leading coefficient is 1 over 1, which is then 1. So I'm going to have a horizontal asymptote at 1. And remember, this only exists as our graph goes out to negative infinity or positive infinity. But I only have one vertical asymptote, so it's going to be fine. Slant asymptote. If I have a horizontal asymptote, I cannot have a slant asymptote, friends. So that would be a D and E on that one. It's got to be one or the other. It can't be both. D and that's a kind of a sloppy N, but that's all right. All right, sketch graph. Yeah, looks like I ran out of room. That's okay. All right, so my vertical asymptote. I have a vertical asymptote when x equals 3. So that looks like a line. It's that x value my graph will never reach. That's my graph goes to positive and negative infinity. So the graph's going to go up at those values. Horizontal asymptote at 1. So when I'm going out to positive infinity or negative infinity, my graph's going to look like it's going towards 1. Let's see here. I don't have a slant asymptote. I have a 0 though at x equals 1. I have an x-intercept at 1, 0. I have a y-intercept at 0, 1/3, so that'd be right about there. And I had a hole at -1, 1/2. So there's going to be an opening here, like a little opening. The graph doesn't connect there, but it looks like it, but it doesn't connect there. I make a rough sketch of it again. And again, I got to go down to -infinity since I'm below. And these will be kitty corners, so that means this graph up here. If I wanted to plug in a value in here, I can make it a little more accurate. But I know it's got to be kitty corner, so it's going to go on the other side. All righty, let's try one more of these here. So the problem you're going to get then, if you don't have your notes printed up in front of you, it's going to look like this: x squared minus 9, and we have 2x squared minus 5x plus 4. All right, why don't you pause the video and see what you can come up with. Go ahead and do it now. All right, here we go, friends. So vertical asymptote. First thing I got to do is I got to figure out, does my graph factor? In this case, let's see here. 2x squared minus 5x plus 4. The denominator doesn't factor. The numerator does, though. So I got x minus 3x plus 3. So since the denominator doesn't factor, to find my vertical asymptote, I got to set that equal to 0. This isn't the most enjoyable thing in the world, because if it doesn't factor, friends, that means I'm going to do the, sadly, the quadratic formula here. So here we go. Oh, x equals a negative b plus or minus the square root of b squared minus 4ac all over 2a. Sweet. Great song. Great song. Oh. Well, friends, when I did my vertical asymptote here, I kind of found out that I had an imaginary value. Hopefully you guys realize that if they have an imaginary value here for your vertical asymptote, that means that it does not exist. There are no vertical asymptotes. There are none. Don't overcomplicate it. There are none. By the way, friends, if my denominator doesn't factor, so it doesn't factor, that means they're not factoring. That means there also cannot be any factors in the numerator it can cancel out with. So that tells me my hole will also be D and E. There will be no holes on this one. All right, zeros. I do have a couple of those I can deal with. Zero. I have two factors there. I have x minus 3 And I have x plus 3, so I'm going to have 2 zeros. X equals 3. And x equals a -3. That was a horrible positive 3 there, wasn't that, friends? I'm telling you, I sometimes struggle with my 3s. There we go. All right. So zeros, I got 2 of them, x equals 3. And x equals -3. Y-intercept, I can find that real quick. I'm going to plug 0 in. So I got 0 squared minus 9 over 2 times 0 squared minus 5 times 0 plus 4. So that means my y-intercept is 0, -9/4, or -2 1/4. Yep. And now we have our asymptotes, friends. So we go and we look at our degrees. By the way, I'm missing something here. Just throw it in there. There we go. I'm going to look at my degrees. Notice they're both 2 again. By the way, if the denominator was bigger than, if the numerator was 1, so it was x minus 9 instead of x squared minus 9, my horizontal asymptote would be 0. But since they're the same, then that means it's leading coefficient divided by leading coefficient. So what I mean by that is I have my degree on top is 2, my degree on the bottom is 2, so that means my numerator equals my denominator. So that means I'm dealing with the leading coefficient for my horizontal asymptote, dividing by the leading coefficient. So y is 1/2. And if I have a horizontal asymptote, friends, that means I would have no slant asymptote. So y equals 1/2. All righty, let's see if we can't throw these out there. I got 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right. We have a horizontal asymptote when my graph is 1/2. So there we go. That means I get really close to positive infinity and negative infinity. I'm going to get really close to this horizontal line, but I'm never going to touch it. I have 2 zeros. And friends, I'll be honest, this graph right here, it's going to be a weird looking one. I would not necessarily expect you to be able to ever have one of these on a test or anything. But just so you're aware, because it is going to look a little bit interesting. And when you go and you graph the dumb thing, it's going to look like this. It's really close, and then it's going to come down and come back up and get belly jumping catfish. Let's try that again. It's going to come down, come back up, and I'll give you a hint. There is going to be a point of, or a relative minimum down here. And again, you don't need to know what that point is. I'll give it to you anyway, just so in case you wanted to make a rough sketch of it. I wouldn't know on my calculator to go find it. because this is a very weird looking graph. So imagine that this point right here is at negative 0.5981. And then that's how far down it goes. All righty, friends. Well, we're about to kind of wrap up this whole thing here. We're just going to play a little bit more with this idea of asymptotes, zeros, intercepts. Okay. We'll go ahead and get rid of this here. Write a rational function with vertical asymptotes at x equals 0, yada, 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 blah, blah, blah. All right, friends, why don't you guys pause the video, see what you can do. Take a guess at this, and then we'll talk about it. All right, so let's see here. Let's see if we can figure this out. I'm going to have a rational function of some sort. I know that they gave me vertical asymptotes. And remember that vertical asymptotes, these are when I have factors in the denominator. So I know that those values have to be in the denominator. So x equals 0, well, that in and of itself is a factor. X equals 2 over 3. Well, to figure out this factor, I'm going to have to put this over 1, like we did last chapter, and I'll cross multiply it. So 3x equals 2. And then I end up with 3x minus 2 equals 0. So let me throw those in here. It says I have a hole at x equals negative 4. Well, let's think about what a hole is. A hole is when the graph has the same factor in the numerator and the denominator. So if x equals negative 4 is my hole, that means that x plus 4 equals 0 is that factor. So I need to put that factor in the numerator and the denominator. And the last thing they give me is a horizontal asymptote. And that was at y equals 5. Well, if the horizontal asymptote is some number, if it's some number, so not equal to 0, that means then that had to be my leading coefficients divided by my leading coefficient. And that happens when the degree in my numerator is equal to the degree in my denominator. So let's take a look at this here then. My degree in my denominator, I got 1, 2, 3. That means I need to add 2 more factors into my numerator. So essentially they would be zeros or x-intercepts. What I have to do though when I add a factor is I just can't add any factor. I have to add a factor that doesn't cross off with something in the denominator. So it doesn't matter what I'm going to use, what factors I use. They just can't be factors that are in the denominator. So take your pick. So let's go, how about x plus 1 would work, and what about minus 1? Okay, now I have the same degree. What is my leading coefficient in my, in my denominator? Well, if I multiply it together, 1x times 3x times 1x, my leading term in my denominator will be 3x to the third. So if I want my horizontal asymptote to be 5, what I'm trying to do is I'm trying to figure out what would be my leading coefficient in my numerator. Well, 3 is my leading coefficient in my denominator. I'm looking for some leading coefficient in my numerator. So that means 15 equals n. That means my leading coefficient in my numerator would have to be 15. Yeah, that's a tough one, isn't it? That's just a little bit of one for y'all to think about. Those of you guys who want to challenge yourselves a little bit more. So on the homework today, or on the bookwork tomorrow, after we get done reviewing tomorrow morning, it's going to be essentially finding asymptotes, finding zeros, finding y-intercept, finding holes. So you don't have to worry about this writing a function too much. That was more just kind of, let's stretch you a little bit. So, hey, good luck, and I'll see you in the morning.